Okay, more of section 11. What we're up to now is to solve problem number 7 here, which specifies that you're supposed to solve it with a ray diagram as opposed to calculating it. And leading up to that, I had put sort of a step-by-step process for people who are, you know, what do I do first? Well, you do step 1 first. So don't know how that got low, and it was aimed just fine yesterday, but I guess that should go up a little. That should be all right. Now, just below the question, it suggests that you want to use 1/10 scale to make it fit on a sheet of paper, okay? With the axis going the long way down the paper, that, well, here's right there. It fits really nicely if you use the suggested 1/10 scale in this way here. But for up here on the whiteboard, so that, you know, someone in the back row could see it clearly, I'm going to draw it full scale because this is a lot bigger than a sheet of paper. So step 1 says draw a line across the page to be the axis. Should probably label this as being number 7. Actually, if you draw it full scale, a meter is not going to be enough. So hopefully I've got that lined up. Step 2, measuring to some convenient scale, in this case, full scale. Draw the mirror, its focal point, and the center of curvature. Okay, this question is about a mirror, so we're going to do what it says in A and ignore what it says in B. So the question says center of curvature is 140 centimeters. Actually, you only need 2 out of the 3 rays to find the answer. And the one I skipped is the one that goes through the center of curvature. So maybe to save a little space up here, maybe I should have done half scale instead of full scale, but to save a little space, I'm going to skip the center of curvature and just put the focal point. If the radius is 140, the focal length is 70. So if the mirror is right there, then the focal point would be there. And since we're assuming the mirror is just a small part of a sphere, kind of like a small part of the Earth looks flat, this is supposed to be a method you can use with just a ruler. A straight line will be fine, even though technically it's curved a little bit like that. And this is the focal point. And if I had decided to include the center of curvature, it would be over beyond the edge of the whiteboard, somewhere over there. So draw the mirror, its focal point, its center of curvature, yes, and the object. That's the thing I'm forgetting. It says the object is 40 centimeters from the mirror. That would be here. On the 1/10 scale that it suggests you use on a sheet of paper, this 70 centimeters would be 7 centimeters. This 40 centimeters would be 4 centimeters. says the object is 10 centimeters tall. So that would be from there to there. Yeah, got that just a little on the long side. We'll just knock a little bit off the end like that. Okay. So step 2, done. Step 3, draw rays from the tip of the object according to the rules above. Any 2 out of 3 is enough, although feel free to draw all 3. When you do draw all 3, they almost invariably do not all cross in the same place because these diagrams are always off a little bit. So something, they should come close to each other, and you go with probably in the middle somewhere. Anyhow, according to the rules we went over yesterday, the ray approaching along the axis bounces back through the focal point. So if that's 10 centimeters tall, it should hit the mirror 10 centimeters above the axis. It's going to be a parallel line. So it approaches the mirror like that and reflects back through the focal point, sort of like that. And then the other one I'm going to do is the one that comes from the direction of the focal point, like this. I guess I should have made my mirror a little taller. So you line up the ruler with the tip of the object and also with the focal point, which would be sort of like that. So a ray that comes from the direction of the focal point should be parallel to the axis after it's reflected. And I really should measure to make sure I've got a parallel line, but I'm in a little bit of a hurry, so I'm just going to eyeball it, or at least this part of it. That takes care of step 3. Step 4, look for where the rays cross, which is the tip of the image. Well, these rays never do really cross. The farther from the mirror they get, they're spreading away from each other. So because they don't really cross, you don't get a real image. But if you're over here looking into that mirror, the rays enter your eye as if they came from someplace back here. Extend the reflected rays back behind the mirror to see where they appear to have come from. And I think I will try to measure that to make sure I get it straight. So that's probably helps to have the ruler right side up. That's a little more than 22 and a half. Let's call it 22 3/4. Nice parallel line, parallel to the axis. It ought to go through that point there. So this is, not that you have to use dotted lines for this to work, but a common convention is to use solid lines for paths that light really does travel along, and dotted lines for extensions of those lines that don't really have any light going along them. So we need to extend this one back also to where it seems to have come from. My ruler's kind of slipping around on me. So they seem to cross right there. That would be the tip of the image. And then you measure your answers off the picture. So for the distance from the mirror to the image, well, I got 79 centimeters. But of course, that's too far away. You couldn't read that. So probably what I ought to do is lie about it and say I got 93. You got to expect these things to be off a little bit. So if this was a quiz and you got like 88 or something, I'd call that close enough, give you full credit. For 78, I probably lost half a point on my own quiz here. Somewhere I didn't get something straight enough. For the length of it, that says 22. You know, it's supposed to be 23. I didn't do so bad on that. I probably bent this a little when my ruler was slipping around on me, or I didn't. Oh yeah, you can see it right there. Well, no, actually it's not so bad, but it does run up a little steeper than it would have if I had a longer ruler and could have lined it up better. As for the character, well, it's a virtual image because the light rays don't actually go there. They just seem to come from there. And it's erect because you look at it and it's right side up. The base was on the axis.
Good morning. Please stand for morning prayer. In the name of the Father.
Okay, well, ray diagrams are all well and good. In an introductory course, they're a good thing to start students out on them because it forces them to actually look at how the lens or mirror works. Here's a picture of what it's doing to the light rays. This is how it makes an image. But as far as practical problem solving goes, they're kind of time consuming, they're kind of inaccurate. It works a little better if there's some way to calculate the answer instead. Well, if you wanted to derive some equations, which I am not going to take the time to do, but just as a quick summary of where the equations come from, they come from the ray diagrams. So this kind of thing here is at the foundation of it all. You start looking around on these diagrams, you find some similar triangles, you know, triangles all over the place on here. And similar triangles have proportional sides, so you can say this is to this and that is to that. And you do some algebra and you end up showing these. Okay. D for distance, H for height, I for image, O for object, and F, of course, would be the focal length. The minus sign is in here because if something is right side up, it has a positive height. If something is inverted, it has a negative height. Also, the image distance can be positive or negative, and that is which side of the lens or mirror it's on. Something, and actually you guys back there might want to get something that should have been printed on here that I didn't actually print on there is as far as the plus and minus signs go for the image distance. Let me write that down. The image distance is positive. Well, it could be a little confusing because with a mirror, the image distance is positive on the same side where the object is. With a lens, the image distance is positive across on the other side of the lens from the object. The way to phrase it that kind of covers everything without having to break it down into this, if this, and that, if that, is to say that the image distance is positive the image distance is positive on the side where the light ends up. In the case of a mirror, it bounces back toward the object. That's the side where the image distance is positive. In the case of a lens, it goes on through, over there on the other side is where the image distance is positive, okay? So either way, it'll be positive when you have a real image. It'll be negative when you have a virtual image. So positive on the side where the light ends up, negative on the other side, behind a mirror, or in the case of a lens, the same side as the object. Okay, so the last thing in this section, okay, you can go back to what you're doing. Just wanted to be sure that you heard that. Solve the same one that I just did on the board here with the ray diagram to get the image distance. Part A. Fill in the numbers we know. We're told the object is 40 centimeters from the mirror. The focal length would be half the radius of curvature, half of the 140. You can leave it in centimeters, you can convert it to meters. It doesn't make any difference. The only thing that matters is you have to, like with any other equation, you have to be consistent. You have to have the same units everywhere. So to solve it for DI, what's left is some algebra. There's two ways you can go with the math. Textbook problems on exams are quite often rigged up so that there's a convenient common denominator if you want to work with the numbers in exact form, treat them as fractions. Your other option, which is probably the way to go when things haven't been rigged up to have a nice common denominator, the other option is to convert these into decimals and handle the numbers that way. Let me just caution you that if you work with decimal, if you've got a calculator that's going to carry these numbers to like a bazillion decimal places, that'll work just perfect. But if you like write things down and round it off, it's better to carry too many decimal places than too few with this sort of thing. If you over round the numbers, it might significantly affect the answer. So if you're going to work with the numbers as decimals, beware of round off errors. But I'm going to use a common denominator here. Or, no, actually, I didn't. Well, if you wanted a common denominator, it would be 280. So you'd have, I guess it would be 4 over 280 minus 7 over 280, if I did that correctly in my head. But looks like when I wrote this out, I just punched it through a calculator. And that minus that came out this as a decimal, which must be equal to 3 over 280, I'm pretty sure. So the other mistake people make sometimes is they forget this isn't the answer. This is 1 over D. You have to do the reciprocal. So there's the location of the image, where the minus sign is there because it's behind the mirror. Which is where you would find a virtual image. So that means it's a virtual image. For part B, the size of the image, HI over HO equals negative DI over DO. Now that I've calculated the image distance, I know 3 out of the 4 things in this and can solve for the height of the image. Multiply both sides by HO to solve it for the height of the image. Height of the object says it's 10 centimeters tall. Image distance was negative 93 1/3. Object distance was 40 centimeters. Minus cancels minus, so the height will come out positive, which means it's right side up. So as far as part C goes, let's shift this over a little bit. Put that over here. Position, size, and character. What it means by the character is basically to answer 2 questions. Real or virtual, erect or inverted. And the real versus virtual depends on whether this came out positive or negative. Behind the mirror means it would be a virtual image. And well, I guess I already answered this. So and another one bites the dust. We are at the end of unit 11. Next week, interference of waves.